All right, let's wrap up why elementary matrices are kind of a big deal here. All right, so we're just going to start this off with a theorem, right, that says a square matrix A is invertible if and only if it can be written as the product of elementary matrices. Right? So this goes back to what I had said a few times before about, we can do row operations on an invertible matrix and get it down to the identity. Okay? So it goes back to that. So how do we do this? Or how do we know that this is true? Okay? So, well, first off, let's talk about what this theorem means. So we have this phrase in here, if and only if. Okay? What that means is that this theorem is bidirectional. So it means if the matrix is invertible, then we can write it as a product of elementary matrices. But if we have something written as the product of elementary matrices, then it must also be invertible. So there's kind of two directions to this theorem. There's a forward direction and a backward direction. Okay? So we're going to prove this because it's a pretty interesting result here. A pretty interesting theorem. And it's really powerful. Okay? So, proof. So, again, there's two directions. We're going to do the easier direction first here. So, this is the implication in the backward direction. Right? The backward direction here meaning if it can be written as the product of elementary matrices, we're going to assume that, and then we're going to show that A is invertible. So what we're going to do here is assume A is written as, say, EK. Well, actually, we don't really need to do that. We can say E1, E2, ... EK. Where we would say where the EI are elementary matrices. All right, so let's assume that's true. Okay? Well, if that's true, then what can we say here? Well, since elementary matrices I wrote that back. Elementary matrices are invertible. Okay, since they are invertible, and the product of invertible matrices is invertible, it follows that FOLLOW, it follows that A is invertible. Right? So again, how does this direction work? Well, we're saying, okay, A is the product of elementary matrices. Right? So each of those E's represents an elementary matrix. Okay? Now remember, we talked about if we have two invertible matrices and we multiply them together, that product is invertible, right? A times B inverse is, or sorry, let me phrase that differently. The inverse of A times B is B inverse times A inverse, right? We had that theorem from before. Well, there's no reason to stop at just two matrices, right? You know, we can multiply together any number of matrices, and that product is still invertible, right? So like A times B times C, the inverse of that would be C inverse times B inverse times A inverse, right? It continues that way. So as long as we're multiplying together invertible things, we get an invertible product. And there we go. So that proves that if it can be written as a product of elementary matrices, then it must be invertible. Now we want to prove the other direction. If it is invertible, then we can write it as a product of elementary matrices. Okay? So how might we go about that? Okay. So how do we do the forward direction? So the one, if we read the statement sort of first, then second. The first thing we proved here was this, assuming the second proved the first. Okay. So in this direction, we're going to assume A is invertible. Okay. Okay, so since A is invertible, since A is invertible, AX equals B. Or let me put some extra words in there. The system AX equals B has a unique solution. Right? Does that make sense? Right? If it's invertible, we showed that it has that unique solution, A inverse times B. Right? In fact, let's even make this a little easier and pick the homogeneous system. Has a unique solution, you know, namely x equals 0. Okay? Just to make our notation a little nicer. Okay. So this means we can use row operations to reduce the augmented matrix A with the 0 vector over here to the identity with the 0 vector here. Right? We can completely, or we can go all the way down to reduced row echelon form, and it's the identity matrix here. Okay? But we're doing row operations, right? So what we're going to do is let E1, E2, ... EK represent, or sorry, let these be elementary matrices representing these row operations. Okay? What that means is then, so we started with A, we do that first row operation, we do that second one, all the way up until we do the last one. And what that means is, well, we get the identity by doing that, right? And that's fantastic. And we know that each elementary matrix is invertible. Okay? So what we're going to do here is just move these over one by one. So we need to multiply on the left by EK inverse. Right? I should have probably put a EK minus 1 there, but right? And then we just want to keep doing this over and over. So we take the second one over. Right, and this will leave us with ek minus 2 through e2, e1, a. And we keep doing this over and over, and eventually we're going to be left with, like e2 all the way up through ek inverse is e1 times a. And the last step, we'll say e1 inverse times e2 inverse, dot, 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 ek inverse is a. Right, so we just keep multiplying on the left by the inverses of these elementary matrices. Right? And I think I actually forgot to explicitly state this, but since inverses of elementary matrices are elementary, right? Think of how we constructed them before. A is written as a product of elementary matrices. And we did it. So this shows that any invertible matrix can be written as the product of invertible matrices. So let's go ahead and illustrate this process with an actual matrix, right? Because it can seem a bit odd how we do that, or how this works. Right. Let's go ahead and go to the next page here. So, example, what we're going to do is take this matrix A, which is, let's say 1, 2, 1, 0. Right, and we're going to write this as a sequence of elementary operations, or as a product of elementary matrices. Okay? So, what we want to do is get this row equivalent to the identity matrix. Okay? So, if I were trying to reduce this to the identity matrix, the first thing I would probably do is swap row 1 and row 2. Okay? So, E1 times A is going to be, we're going to swap row 1 and row 2. All right. So if we swap row 1 and 2, that gives us this. Okay. Now, let's see, this is E1 here. Right. Now, my next step is I want to get rid of this 1, so I'm going to do row 2 minus row 1. So E2, E1A. So I'm going to just write E2 here. We're doing row 2 minus row 1. So we do row 2 minus row 1 here. I'm going to copy down the E1A from here. All right, and this is going to give us 1, 0, 0, 2. Okay. This matrix here is E2. All right. Now we need to do one more operation. This is E3, E2, E1A. Right? What do we need to do to this matrix? Well, we need to divide this row 2 by 2. Right? So 1, 0, 0, 1 half. This is our E3 right here. All right, and again, I'm going to copy E2, E1A and put that here. 1, 0, 0, 2. Right, and if we multiply this out, we'll get the identity matrix. Right? So what we have here is that E3 E2, E1, A is the identity. Okay. So that means that A is going to be E1 inverse, E2 inverse, E3 inverse. Right? Because we just keep multiplying on the left by the inverses of these matrices in order. So we have to do E3 inverse first, then E2 inverse, then E1 inverse. So we see those show up in the opposite order. Okay? And now we can compute, or we can say here that A is the product of, right, let's see, E1 inverse. Well, this is a swapping of rows, so it's its own inverse. Okay. E2 inverse, what did we do for E2? We did row 2 minus row 1, so now we need to do row 2 plus row 1. Goes to row 2. This will be 1, 0, 1, 1. E3, we divided row 2 by 2. So here we want to multiply row 2 by 2. Okay? And let's, just for sanity here, let's check that this product really is A. Okay? So we would multiply, say, the first two matrices. So 0 times 1 plus 1 times 1. 0 times 0 plus 1 times 1. 1 times 1 plus 0 times 1. And 1 times 0 plus 0 times 1. Okay. And if we multiply these out, we have 1 times 1 plus 1 times 0. 1 times 0 plus 1 times 2. 1 times 1 plus 0 times 0. Oops, that was a 1. And 1 times 0 plus 0 times 2. Is that our original A? It is. Excellent. 1, 2, 1, 0. All right. So here, we've shown that the matrix A is this product of elementary matrices here. All right. Fun fact, by the way, we also get the inverse of A. So if this is A, this part right here, this product of elementary matrices is A inverse. So A inverse is E3 times E2 times E1. So I'll let you multiply that out on your own and figure it out. But these elementary matrices here, they're really powerful. They let us get the inverse in a pretty low-level way. Right? So hopefully that makes sense. Hopefully you can kind of see how this is neat here. So to wrap this up, I know we've kind of gone on a bit here in this video. But let's wrap this up and sort of summarize all the stuff we've been talking about. Right? So, a theorem here. So here, if A is an n by n matrix, then the statements below are equivalent. Right, and we're going to actually later on add 2 more conditions to this. But first one is A is invertible. Right, what this theorem is going to tell us is what sort of things are equivalent to being invertible. Well, one of them, as we talked about, is the system of equations AX equals B has a unique solution for every n by 1 matrix B, or column matrix B if you want. Okay? So every system of equations you can make out of the invertible matrix has a single unique solution. Okay. In particular, the homogeneous system has only the trivial solution. X equals 0. Okay? Or A is row equivalent equivalent to the n by n identity. And 5, A can be written as a product of invertible matrices. Right? So it's pretty important that we have a bunch of different ways to check if a matrix is invertible. Right? And like I said, eventually we'll add 2 more to this list, but that's it for now. Hopefully this all makes sense here, or you can start to digest it at least. And yeah, we'll see you in the next one.